hopefully you all visited Kelly's talks a few minutes, like about 2 hours ago, on speech recognition and speech synthesis. A lot of that work is related to solving that particular problem, and that's a very important problem for Mozilla and generally for the world, because these technologies sort of live in these silos, and we want to break them open and make them available to everyone. So this is in addition to that work. So these are things that we've been exploring, other applications of machine learning. And some of this is technical, but some of it is also, we're looking at ways to take this technology and put it in front of people, right? Like get them access to, how do people get to touch and experience machine learning in products? So some of the discussions will be around that. So what is the big picture? So we want to really build and improve products by creating privacy-respecting, ethical, and open machine learning. When I talk about privacy, really in terms of what I really mean is we want to be able to do a lot of machine learning on device, right? So this includes people take these very large models and shrink them down and make them possible to run on device in a way that they don't leak information, right? So and more recently, my Alexa keeps popping up and sending things to the cloud without me realizing what's going on. So we want to really solve this problem. That's one of the core tenets of what we're trying to do here. We also want to be transparent about our data policy. A lot of these models also have sort of inherent bias in them. So, one of the demos we're going to show you later is, we trained a grammar checker on some data sets, but one of the data sets that I was able to find, able to train on, was a corpus of Japanese learners of English. So if we were to train that model on that particular data set, it would be biased towards that group of people, right? To combat this, we really need to collect a lot of data from a lot of different kinds of people, a lot of different cultures and languages, to be able to create models that are effective and that serve everyone. And of course, we want to make sure that we build models that keep people safe, and they cannot be used for evil. Although, unfortunately, it's hard to predict. So sometimes these things are. And lastly, we want to publish our data, our models. So with deep speech, we're publishing our deep speech model. Now we're working on speech synthesis, but once we're done with that, we're also trying to make that more available, and as well as the data that we're using to train some of these models. So that's the Common Voice project you may have heard about. When we're looking at, there's so many things you can do with machine learning, right? And like just today I found out there's a machine learning algorithm for predicting memes from images, right? Like the question is, that's fascinating, it's interesting, and I've gone through some of those and they're quite funny. But should we do that, right? Like, I don't know. Like, there's so many things you can be doing. Use machine learning to build products, like saying, use a computer to build a product, or use software to do things, right? Or use a database to do things. So we want to be sort of, careful about like how we apply machine learning and what kinds of things we take on. So in this vein, we're looking at 5 different areas of product explorations around machine learning. One is in the area of voice assistance, and I'll talk about that in a second. The other is content assistance and language assistance. And this is a slightly different definition of typically what people say about language assistance. The other is voice control, and lastly, machine learning as a service. And these 5 different areas are kind of guiding us along a path of exploring new products. So there are new products we can build, but there are also opportunities to improve existing products that we have. And lastly, once we kind of decide like what kind of interesting products we can build with machine learning, we have to be honest with ourselves. Like, where do we get this technology? Like, do we build it ourselves, or do we go out and make use of other existing technology that's out there? And for some things, we think that we should be building it ourselves, like speech recognition and synthesis. That's very core and important. Others may not. Maybe we can, we can purchase it or use it from somewhere else. When these areas, the way we identify them is we want to be able to explore areas where machine learning is a differentiating factor. In a space where if you were to apply machine learning, you can actually leapfrog existing technologies, right? We also want to make sure that we can solve the privacy problem in that particular domain. And lastly, we want to make sure that we can scale to a large number of people, a large number of languages, without having to do, like, we don't want to scale linearly. We just want to be able to apply the same technique just be able to collect new data and apply the same algorithms and be able to create products for people in those areas. So one of the sort of general themes is voice control. So the hypothesis here is that voice UX, so interfacing with the device through your voice, is an actual product differentiator. And this may be true for things like Alexa and Google Home, and we're exploring sort of use of voice in that space. So one of the areas you might have heard about is the Scout project. And this is sort of using voice to see if we can interact with and read websites or be able to read Pocket articles or even control it, right? So if your hands are not available or you're like biking, for instance, you can still access some of this content through your voice. There are other interesting applications of voice in this space. One is podcast listening, for instance. Like podcasts are very popular and they're actually probably becoming more popular. And there are interesting things you can do with controlling and playing podcasts, right, with your speech. But it's not just about saying, play me the latest NPR podcast. You can also do things like, hey, set a bookmark at this particular location. Or through speech recognition, you can identify various parts of the podcast that may be referring to other topics or maybe referring to other episodes of the podcast, and we can identify those and then sort of give recommendations or create links within content that we're maybe exploring. Lastly, there's things like VR, using speech recognition in VR, right? You don't have access to your hands. I mean, you do, but you're using, point at things, right? You don't have a keyboard, so you might want to use voice in that space. And we're looking at, shipping some of these features, not, as mobile, but also on desktop applications, right? So integrations in the Scout or Pocket. Do you want to give you want to speak briefly about these?
Yeah, so these are two applications that use voice control now. So this first one is called Digital Race Engineer. The idea is if you're racing in VR, you have like
Car 19, our leader is behind you currently -0.1.
But you can't see the buttons because you don't
1
have set
minute,
off.
44.977
all the
yards
stuff in the
left.
car with your voice. So which tires to change at the next pit stop.
Great, fastest lap, 1 minute, 43.7.
And this is a similar thing for a game called Elite Dangerous, which is basically a space flight simulator.
Max weapons.
Deploy weapons.
Deploying and readying weapons.
And it has
Target
a
hostile.
billion things that you can
Lock
do.
target.
So doing it with your voice is helpful even if you're not in VR. And the interesting thing there is they actually went and recorded William Shatner and a whole bunch of other famous people, so that the voices of the ships in the game are
Launch
recognizable.
countermeasures.
Thanks. Okay. Another area of exploration is this language assistant space. So we think people have value comprehension and reading tools when it comes to writing text. There's a very popular extension, I don't know if anybody here uses it, but it's called Grammarly and has about over 10 million users in Chrome extension store. So it's an incredibly popular tool for effectively checking your grammar. But there are many different tools in the space that are actually pretty interesting. So spell checking, although it's quite boring, but it's an interesting problem. A lot of the Google searches are actually, purpose of spell checking words. Grammar checking is one of them. Thesaurus, dictionary, language detection, language simplification, Smart Compose. I don't know if you've seen some of the latest announcements from Google where you can be authoring an email and you get completions of your email as you're typing. Translation, of course, speech to text and text to speech is sort of an application of speech, but in the space of language assistance. Another one is, I guess I don't have it here, but it's summarization, right? So that's also an interesting application of, something that kind of lives in this space of being able to work with text more effectively. And possible ways of shipping this as a product is either an extension of Firefox or as an extension in Google Chrome Store, for instance, or as a standalone product. Now, Grammarly is obviously a competitor, but there's also interesting, if you look at dictionary.com, is a very frequently visited website, right? So there are quite a few players in the space. Another area that's kind of fascinating is content assistance. So when you're, be able to time stretch different music or audio, or I guess you could apply it to you can imagine as a text article, the time stretching in the sense that you're summarizing it. But being able to work with video and audio to extend it to certain dimensions. If we're looking at decentralized web, things like nudity detector, profanity, fake news, these are some of the technologies you have to run locally on your machine. You don't have to rely on some centralized place where these models run. So can we do some of these things locally? Noise suppression is another one that's interesting, is applying machine learning to reduce noise from audio. And we'll give a demo of that shortly. Text extraction from images and video. Oftentimes there's a growing number of videos on YouTube, for instance, where people will screencast their work, right? But then if you actually want to follow along, maybe you want to copy and paste content from a video into your editor. You can't really do that because it's a video. So there's interesting things around, can we enhance that content in ways that we can extract information out of it and make it actionable in some way. 3D reconstruction from 2D images. This is kind of an possible interesting use case of applying machine learning to create some sense of depth from 2D images. And this has an interesting application for perhaps a VR browser where you have stereo vision. And lastly, we also considered things like machine learning as a service. Can we build some of these models and host them in the cloud and give people access to them? There's many things we can do, of course, with speech to text and text to speech, summarization, translation. Another interesting aspect of it, if you work in this space a little bit, is you might have a great idea and you want to get access to a data set. And then very shortly, as Kelly can tell you have to go through all these legal processes to figure out, can you actually use this data? You have to sign a PDF, fax it in somewhere. It's really difficult. So by the time you're done with this, you just want to stop working on the problem, right? So is there an opportunity to have a place where we can gather and collect data and allow people to train on that data in a way that doesn't let their data be extracted, so they can try out algorithms on maybe closed data sets? Okay, so I'll let Jack give you a quick intro to machine learning, and then we'll switch over to Jean-Marc.
Okay, so I just wanted to give you guys sort of an overview of the different techniques, sort of behind the scenes of how these things work, because they have some bearing on the kinds of problems that you can attack with them. So why is this deep learning stuff so popular these days? It's really because this technique of machine learning scales with the amount of data you put into it, where the previous stuff that we had didn't. So you just keep adding more data and the models get better and better, which is sort of interesting because now if we want to take these models that maybe didn't used to work, we can just throw a whole lot more data at them and now they'll maybe work. But it also creates this weird incentive where if you want your models to be the best, you need to be sucking up every bit of data that you can, which is sort of a perverse incentive for sort of the kind of data surveillance stuff that Google and Facebook and others are doing. So the way these work is they're a network of sort of, they call them neurons, but basically this X1, X2, X3 are your inputs, and you have sort of this hidden layer of stuff that you don't look at it and does some calculations, and then you get some output. And each one of these, A1, A2, A3, each one of these neurons has some weight attached to each of the inputs, so they're all fully connected. And then what you end up with is this big matrix full of numbers of all these weights. And then, so you take, you have your input, which you know what the values of X1, X2, and X3 are for your problem, and you know what the output is supposed to be, and you just run this through the network. So for training, you initialize all those weights completely randomly. So you're going to get nonsense answers, for example. You tell it what the inputs and outputs are. You compute a loss function, which is basically like, okay, if it's predicting something between 0 and 1, you can just subtract what it predicted from what you think the real answer is and just sum up over all of those predictions and get the loss. And then we just use something like gradient descent to figure out how to modify all the weights in order to decrease the loss function, and we repeat this millions and millions and millions of times, and each time it gets a little better, the weights get a little better, and our predictions get a little more accurate. So this is what the loss function looks like if you were to plot it. Well, I mean, it's like a hypothetical loss function, And gradient descent, basically, you know, you're going to end up starting at some random place on this. You're going to figure out like which way is downhill, and you take a tiny step downhill. And then you rerun that whole training loop again, and figure out where you are on this slope. And you take a tiny step now where you think downhill is now. And you just keep going, and hopefully you end up at the bottom somewhere. So they just get better over time. The interesting stuff happens when you connect a bunch of these up. So this is why they're called deep learning, because basically GPUs allowed us to have a whole bunch of these connected together. And sort of the intuition here is that the early layers learn like very simple things about the data, and the later layers learn more complex things about the data. And I'll have an example of that in a minute. And so this would be like a network that maybe classifies something. So you have 3 inputs. Like, for instance, if you're trying to figure out if one of these deep learning technologies that we're exploring is a good product idea, like maybe X1 is like how many users do we think that market will be, X2 is like how much revenue we think that market is worth, and X3 is maybe how ethical it is, right? And we're going to predict whether Mozilla should, you know, spend time and invest resources into this product, right? So, and it'll maybe be a classifier for that kind of problem. A different kind of network is called a convolutional neural network, and these get used often on images. And basically what happens is we use these convolutions, which are basically just like these little filters, which are these matrices of numbers, and basically you just apply that to every pixel in the image in order, and it generates something like the feature map on the right. And the idea is, like, people have used these convolutions in graphics applications for a long time for problems like edge detections and things, which is sort of what that one is doing over there. And the interesting thing is that in machine learning, what we do is we're going to have a bunch of these convolutional kernels, and each one is going to generate one of these feature maps, and we'll just run a whole bunch of them and stack the feature maps together. But the thing is, we initialize them randomly. We let the network learn what the best convolutional filters are to extract some representation or some meaning out of the input images. And then it goes through a couple of these layers. So after you do convolutions, generally you want to shrink the data size down so that each of the later networks gets sort of smaller and computationally tractable. And then at the end you have one of these sort of fully connected networks that does the classification at the end. And these get used a lot in, like I said, for images. The deep speech and the text-to-speech both use these convolutional things because they work with spectrograms, so that like we transform the audio into 2D images of the waveforms and then run convolutional nets on those, for example. So this is sort of a visualization of what kinds of things activate different neurons in one of these convolutional layers. I think this was trained from ImageNet, which is like it tries to classify all the objects in the image and tell you where they are. And so you can see like this is from layer 0 on the left, and you can see it's basically trying to detect edges and solid colors and things like that. In layer 1, you can see there's slightly more patterns to things, like if it's striped or if it has circle shapes in it. As you go farther into the network, it gets bigger. So like this one's sort of like detecting feet and things with holes in them. And as you go farther along, you get to things like, you know, this is detecting dogs or flowers and things like that. So so it's learning sort of more complex representations deeper in the network. This is really nice for convolutional ones because you can sort of visualize it by putting sample pixel values in and seeing what neurons activate. For the other kinds of networks, like we literally have no idea what those neurons are doing, right? Like it's totally opaque what that representation means, which makes them really sort of hard to debug and reason about in the interior. So the next one I'll talk about is recurrent neural networks. These are also used in our text-to-speech and speech-to-text models. But basically the idea is you have one of these networks in the box here, and you're going to feed it in a sequence of things over time, and it's going to give you a prediction out over time. But every time, you're going to feed the prediction it gave you back into itself and run it again for the next time step. So at x2, you're going to get the value that you got from the first time step A1 and x2, and you're going to produce a y2. And the cool thing about this is it lets you do sort of arbitrarily linked sequences So for instance, in text-to-speech, we're inputting characters down at the bottom, and we're getting out waveforms out at the top. Or in speech-to-text, you're putting waveforms in at the bottom, and you're getting characters out at the top. And the sequences don't have to be the same length. Like you can read in a bunch of these things and then output a bunch of these things. There's all kinds of ways you can hook this up. So we have a system for doing classification. We have a system for dealing with images, and this one lets us deal with sequences. Another cool thing that you can do with these things is called transfer learning. And basically what you do is once you train one of these networks and you have all of these weights and you have your model, sort of, it's just giant binary blob, for example, you can just take a model that you did for one job and you can start training it starting from those weights on a different job. And for some tasks, you might have very little data for some specific job, but a whole lot of data for a more general task. So you can train one for the more general task and then sort of specialize it for a smaller set of data. This is pretty cool. I actually am using this currently in an experiment where I took the text-to-speech model that Aaron wrote and trained it on the same data set that they've been working with, and then I tried to train a new speaker from the trained thing of the old speaker. And it actually seems to work better. So I'll keep playing with that. But this is kind of cool because why, it doesn't seem clear to me why you should be able to just take these weights for one problem and apply them to another, but it just works. The last one I'm going to cover is the generative adversarial networks. And these are really cool because what you do is you hook up something that generates something. Like for instance, if we're going to do one that makes fake images of people, you make a generator that can generate fake images of people, and then you take a set of real images and you feed either one of the fake images or the real images to another network, and that network is trying to detect whether your image is fake. And so you know the true answer, and so you can compute whether you got it right or wrong, and then you can use that data to feed back into both networks to update both of their weights and train them against each other. So what you'll end up with here is something that's really, really good at generating fake images and something that's really good at detecting if you've got a fake image. So these are pretty cool. I haven't had a chance to play with these yet, but I have a lot of cool ideas for what we could do here. Okay, and Jean-Marc's going to talk about some of the applications.
So I'll describe two applications that we've been playing around with for now. I've already talked about those, but I'll go into a little more details. One of them is, one of them is called RN noise. The idea is to do noise suppression using deep learning. So the way traditional noise suppression works is there a laser in there? Oh, okay. So you've got a noisy signal coming in, and first thing you do is you apply some voice activity detection to figure out which part is noise, which part is speech. When you have noise, you know that you want to build your noise model. So you want to know exactly what kind of noise you have. And using that noise model, you know what to subtract from the signal. And with that, you get the noise speech. And those things have been around since the 70s. The problem is each of these blocks is incredibly hard to tune. You have fancy estimators with lots of constants, and you listen to how it sounds, and if I tweak this constant, it sounds better, but this file is worse. And it's really big pain to tune all of that. So the idea of deep learning is instead you go with, it's data-driven, basically. You've got sometimes millions of weights in some models for more complex tasks, and you just learn from the data. And in the case of RN noise, the idea is to not throw away everything we were doing before that with signal processing, DSP, but instead have a hybrid approach that does both signal processing and deep learning. So the idea is to use DSP techniques for everything that's straightforward. We've been using the fast Fourier transform for decades, and it's still good enough. There's no need to learn any of it. So we can use DSP for that. But then all the complicated estimators that require a lot of tuning, we can actually use data to tune all of that. And it becomes a lot easier to build these systems, and they also perform a lot better. And in the case of our noise, the idea is to reduce the complexity by only dividing the spectrum into just a few bands. Instead of saying we have this full spectrum with 480 lines and training neurons on each of them and having huge models that take megabytes and run barely real time, what we have here is just 22 bands. So we use actually the same bands as in the Opus codec, which are very close to what we call the BARC, the BARC scale. And with just 22 bands, we decide for each band how much we attenuate and how much we keep of the signal. So the way the architecture is done is very similar to the traditional models that had the voice activity detection, the spectral estimator, the spectral subtraction. In this case, we still have sort of a voice activity detection with some fully connected layers, and GRU is a recurrent neural network. The activity detection gets fed to another recurrent network that estimates the noise, which also feeds data to the last box that does the actual spectral subtraction. And in the end, we end up with just 22 gains that tell us when to attenuate the signal at what frequency. So here is basically a spectrogram of what we get. This is the noisy audio. So we can see a lot of noise, especially at these frequencies, but also the green at low frequencies. And the denoise speech is there. And below would be the perfect solution. So, we're not quite there, but it's pretty decent. Where's the web page? So I'm going to play a few samples here. So first, what is usually considered easy noise, like car noise.
In the course of a December tour in Yorkshire, I rode for a long distance in one of the public coaches on the day preceding Christmas. The coach was crowded both inside and out, with passengers who, by their talk, seemed principally bound to the mansions of relations or friends to eat the Christmas dinner.
And something that's a lot more challenging for many algorithms is called babble noise.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so. The simplest method is to mix the medicine with butter or some other grease and smear it on the nose of the animal from time to time. Naturally, it will lick the grease off, and in this way will swallow the medicine.
So it's not quite perfect, but we can get a lot of noise reduction. And I won't play the other sample, but some time ago I worked on non-deep learning based noise suppression, and this was far less work and it performed a lot better. And so here I have basically sort of curves of quality versus signal to noise ratio for different noise types. And essentially the improvement is about double what you get with a normal non-deep learning based noise suppression system. So that was for noise suppression. Another thing we've been playing with recently is it's a project called Deep Proof. So it's a system that corrects both spelling and grammar. It's working for English right now, but it could be applied to other languages. So the idea is to learn to write through data rather than explicitly coded rules. So it means no language-specific tuning. You have misspelled text, correct text, and you have a model that learns to transition from one to the other. The idea is to do local inference to not have this run on a server, so it needs to be low complexity enough to run on a regular CPU or even a mobile CPU. And because we're dealing with misspellings, then we actually use characters rather than word models, because the words could be completely misspelled, so we can't model that. In terms of how it works, so Jack talked about RNNs and what they could do for sequence. So this is an example where the input sequence may not be the same length as the output sequence, because maybe some words got omitted, maybe some words were there twice, there's a missing S or an extra S. So the idea here is we've got corrupted text as input. We use character embeddings. So each letter gets represented as a vector of a certain number of floating point numbers. We use convolutional networks at the beginning, and then bidirectional LSTM, which is a type of recurrent network. And that is part of what we call an encoder. So typically these systems work as encoder-decoder. For example, machine translation systems also work like that. There's an encoder that absorbs all the text in one language and a decoder that synthesizes it in a different language. So in this case, our encoder processes the corrupted text, and the decoder works in a loop. So every time it outputs a character, it feeds that back in for the next character. So it predicts one character at a time. The LSTM here, the recurrent network, it tries to predict the next character, but it's also helped with an attention mechanism that looks at what the encoder outputted. So presumably the text we're synthesizing is highly correlated with the input text. So we need to look at what the encoder saw and direct the decoder into producing something that looks like it, but as actually correct grammar. So the output of the attention mechanism gets fed again to another layer of recurrent network, and then we found an output character. So this runs in a loop, one character at a time, and we actually synthesize a correct sentence out of that. So the key here is to actually get good data, which is always the problem with machine learning. In this case, for grammar, it's not a very popular topic, so there aren't many well-known data sets for that. So one way to work around that is to actually use synthetic data, which is not always an option, but in this case it is. So we can start from a lot of presumably correct text from Wikipedia. We assume there's not too many mistakes in there. And then we can actually inject mistakes. So rather than code very complex rules about how to correctly fix the grammar, we can use sort of reversed rules just as how to randomly corrupt data. And that's a lot easier because there's tons of ways to corrupt it and only one way to fix it. So with that incorrect data, we pick something like 12 million chunks of 300 characters from Wikipedia, corrupt it with plausible mistakes, and have the network train on that. We can also get some amount of real-life data. There's a website called Lang8 where people learn to write English, and other native speakers correct what they write. So we have some amount of real data that we can add for more realistic mistakes. So the two combined together can do a decent job. And the holy grail here would be to actually use the data from everyone who uses the system, but without having everyone actually, upload all their documents. Like if you're writing a legal document, you don't necessarily want to upload that to a server. So ideally, each machine would be able to learn how to make the system slightly better and send that to a server, but without the actual information about what was written. Only slight change of rules or slight change of weights into how to do a slightly better job. Want to do the demo?
Oh, sure, yeah. So we put a demo together we wired up the grammar checker ultimately want to run this locally, but for now, since we haven't done that part yet, we just put it on a server somewhere, and you can try it out yourself. So this is live demo time. Cross your fingers. Okay, so I don't. Can someone give me a poorly written English sentence? Me speaking. Okay. I need. Can you? Actually, I can just speak loud.
You're covering this.
Oh, sorry. All right. Well, let's make this bigger. So give it a few seconds. So it sends a text to server, and actually what it comes back here is a sentence that it's a diff of a sentence, right? So it comes up with another sentence, and we have to figure out suggestions. So here it's saying I should replace me with I. Now, what is happening is that as soon as we make a suggestion, we will send the text back to the server, and it'll come back and give us a correction. So it may actually change some of the other parts of the sentence. But for instance, here it says, if I were to replace both, so it would say I, and is speaking English, and suggest that I correct it to am speaking English.
If you replace is by are, will it change me in we?
So let's see. Me to we.
No,
No.
if you put R instead of M.
R is still.
Yes, are. No, let me and
Me are speaking
me are
English.
speaking. Yes.
Vice President speaking English. So the interesting thing here is that it doesn't know anything about grammar or words or anything. It just like spits out characters one at a time, right? So in some cases, that's right. So, do you have a question? Sure, yeah, come over.
Okay, yeah, sure.
Whoa, forget about that.
Let's see, co-reference. Do I have to do anything? Oh, it's
No,
just
it likes all of it.
it
It's
likes
not.
all that, okay.
It's got limits into what it can infer from.
Okay, so it's not going to do any kind of long distance agreements or anything like that.
I mean, theoretically it could, but right. So right now the main limitation is it's learning from mistakes that I feed it.
Okay.
So presumably very few people have made this kind of mistake, so it's not going to fix it. Or, I mean, most of the data is still data that I generated from Wikipedia. So, for example, among the rules for distorting text that I have is, switching between me and I, or am and are and be, but not changing genders, for example. If I added the rule for changing gender, it might have picked it up. I don't know if it would have, but it would have a chance at least.
So, right, you can also figure out if two words are joined together, it can split them up. Okay, so feel free to try it out. It's called, we have this really complicated code word for this project, so it's called 0.app. You can try it out on your phone. So one extra thing, since we have time, that Jean-Marc touched on for a second, is federated learning. So if you want to build a machine learning model and want to actually deploy it, put it into product, right? So you have three pieces you got to worry about. First, you need the data. Then you need the algorithm. Then once you get the data and algorithm together, sorry, it's a little blurry, and then you produce a model, right? So now you want to publish this, right? So generally what you do is you say we want to ship let's take a concrete example. You want to ship grammar checking in Firefox, right? So, but we cannot get it. So one model would be, how does this laser work, right? So we gather a bunch of data, we build the model, which the algorithm which produces the model, then we produce a model, and then we sort of have this layer where Firefox communicates with the model in the cloud, and it sends up some text. The model replies back with some corrected sentence, and then we make it work. Unfortunately, when you do this, right, you communicate with the model, and you're actually sending the model your sentences. So that's a privacy problem, right? And also, if you want to improve the quality of your model, you need to gather more data. So how do you do this? Like over time, in this model, poor choice. In this architecture, I suppose, I guess that's what they call it, architecture. Over time, you really want to extend the model, right? So you're collecting more data, you use the same algorithm, you train a larger model, and so forth. So over time, this will get better and better in quality. One approach would be to have some existing set of data, we train a model, and then we deploy sort of smaller versions of those models to every single copy of Firefox, right? So I drew them smaller, but they still can be quite sizable. So for instance, today, the grammar checking model is about 150 megabytes or so forth at the moment, but we can shrink it down, the current latest copy.
Right now, it could shrink down to about 50 meg.
Right, so like the really unoptimized version of it, it's like, it's in text representation, it's about 150 megabytes. We can shrink it down. The point is that as it gets better, more quality, like it'll still take some time to deploy these models. The difficulty here is that there's no way for Firefox now in this structure to communicate back with us to create a better model. So one of the ideas that we're sort of exploring is this notion of federated learning, where we start off with some data set, we create an algorithm, we create a model from that algorithm with that existing data set. And then we pass on to every copy of Firefox both a smaller model along with the algorithm that was used to train that model. And then we rely on the local data produced by a Firefox user, right? Like say they use the model and they make a correction, or we give maybe 3 different options for corrections to make, and we can take that information, we can save it locally so that we may use, so that the user may use it another time to retrain the model. And then the local model on the machine gets trained with additional data. And then the idea is that can we take this additional new model? It's like like model prime, I guess. And then can we send this back? Can we send instead of sending the data, we send differences in the model. So can we sort of take the experience that this model has learned and feed it back to this centralized model to get it better over time? Now there's obviously interesting questions here. Is this like privacy preserving? Can we prove that this is not leaking any personal information? Those are questions we need to solve. This approach is used by Google, I believe, for their I guess sentence completion verification on when in their keyboard apps. But we're hoping maybe the same model can be applied to us for in effect, make sure that we can rely on data generated by browsers, but in a way that does not leak or violate any privacy concerns. Now the question is what if Jean-Marc comes next week and says, "Oh, I thought of a great new way to train this model," and this new model that gets generated by this algorithm is not compatible with the current existing model that's been retrained on a local machine. So in this model, in this architecture, what we would do is we'd take the existing data that was collected on a local machine and then retrain the local model, or maybe take the existing model that was there and somehow figure out a way to feed that information back to the newly trained model. So this is one approach to trying to solve this problem about getting access to data to be able to train models. Okay, I think that's all the slides we have, so if you have any questions. Thank you. Also, so part of this exercise is that this is a very interesting space, and there's million problems we can tackle, and we'd love to get your feedback and experiences and the kinds of problems that you want to solve. and bring them forward. Like, we'd love to hear the kinds of things that you'd like solved. Yes.
Perhaps this is similar to your federation thing, but I was thinking, for me, the names of my household members, certainly mean something very different, if I'm using my speech system than somebody else. Is there a way that I could train just the early layers of the network to know, in this installation, these particular words have this meaning, whereas they may not generally. And then without sharing that anywhere, so I don't want that going out of my system, be able to make use of the rest of the training network.
So this, touches upon transfer learning a little bit, right? So you can add additional data to it and train that way. I believe this is similar for something on speech recognition, Kelly, if I'm not wrong. Like, then we tried something similar where we pre-trained a model, and then we added additional, I guess, like checkpointing. So you can train a model up to some point, and then you can add additional data to it and train it into a different direction. There's interesting work from Google where they do things where, you can train a model that can detect, that has enough information to be able to detect, say, objects, right? And then you add additional layer to the end of this thing, and then you can train that to if it's a red object, do something, otherwise blue object, do something else. So you can add additional data to it to train in a different direction, but it's sort of building off existing expertise that it's pre-trained some ways. Right. Another bit I didn't talk about too much at length, but the other question is, if we're going to try to run an algorithm locally in Firefox, right? Like, we're not going to have access to a GPU. Like, how do we run this efficiently? So in the demo that Jean-Marc had, he was doing inference. Well, we did the inference and we saved the audio, but we also have a live demo of doing inference in the browser running WebAssembly live. But the question is, can you do additional training in the browser through WebAssembly, for instance? Or if you have access to a GPU, we can probably do something interesting there. Yeah, so the Google's TensorFlow JS thing is a re-implementation of TensorFlow operators using WebGL. There's also work from someone that did that compiled TensorFlow to WebAssembly, so ran that on the CPU. So that should be doable as well, but I'm not sure what the. So the question is, there security risk in terms of, so there's a privacy issue, but there's also, I guess, suppose a security issue, right? Where, yes, possibly. We haven't worked out that. I suppose, I think you can also do, if you can take a subset of, you can do sort of randomize, which ones you're going to collect, or you may do some kind of voting mechanism to see if they actually take your model in the better direction. Do you want to add something to add?
The other thing is it's easier to validate the model than to train it. There's usually some holdout data that you use to test if your model is performing well. So when you get these delta updates, you could run it through the validation and see if it actually improves and throw it away if it doesn't. If it doesn't change much, then maybe it. That could be. Of course, you can store the old ones. I guess someone will figure out some way to do something terrible, right? Where, we'll change it so that it grammar checks everything to write Nazis where it shouldn't write Nazis or something. But it's not clear to me what that attack vector is. So we'll just have to.
Mostly all the updates are presumed to be small. So, this thing is usually called stochastic gradient for a reason. So, it assumes there's going to be noise and gradient pointing in all different directions. So, assuming the update is small, no one update can cause any damage. Of course, if 50% of the updates you get are really bad, then you have a problem. I mean, then you would need to have like the same kind of countermeasure that presumably everyone has. Like for example, Google, if you have one user that would send like millions of requests where it really wants this page to make the page rank go up, presumably everyone's tried that and they have a way against it, so we would need to guard the same.
I mean, we're going to get a lot of new attacks on these things, just like the ultrasonic activation for Alexa and things like that. People will come up with novel ways. I feel like we're in the beginning now, like when we added JavaScript to the browser, where like, hey, look, there's all this awesome stuff we can do. And then we had like the moment of panic where like, oh my God, there's all this awesome stuff they can do. and now we're sort of in this sort of better phase where we think we're at least somewhat safe and dealing with active attacks when they happen. So we're not there yet. We're still in the this is amazing phase, and we haven't gotten to the trough of disillusionment or whatever.
So just to be clear, like none of this, this is stuff we would like to do at some point. We've not directly touched any of it. I have looked, for example, at the Lang 8 site that actually has pretty unreliable data because sometimes you have the bad text next to good text with extra typos, or sometimes the good text also includes a comment. So we've been looking already at ways to filter that. The fact that part of this is a language model, you can basically run an existing model on the presumably correct text to see if it thinks it makes sense as correct text or if something's really wrong with it, in which case you can exclude that sample if you're not confident enough.
So like what you're talking about is kind of overfitting, I guess. Like if it learns some feature so well and then try to apply it. So there is a method called dropout regularization where whenever you have one of these recurrent neural network nodes or one of these other nodes, you actually, when you do a training step or when you train a batch, you'd like randomly pick half the nodes and those nodes don't exist in that run. And that kind of prevents one node from learning to over rely on some other node. So you can sort of regularize the network that way. And there are a couple other techniques that you can use to sort of make the network robust.
That defeats over fit, but it doesn't, it's really redundancy, a redundancy within the interfaces themselves. They're learning, if you look at the amount of...
If you mean if they both learn the same function?
Yeah.
Yeah, so one interesting thing is if you don't initialize the weights randomly, like if you initialize them all to the same value, like they never learn, like they all learn the exact same thing. So I think, maybe Kelly knows more about that, but...
In practice, like, you'd never have two neurons that are exactly the same. So typically, one will dominate the other at the next layer, and the other one will start learning something else. Like, I've not seen that being so much of a practical issue to have, like, nearly identical neurons.
The other thing that there are network architectures where there's like skip layers, where the neurons in like layer 2 will skip ahead 5, and so they can sort of fast forward information later on, and that sort of prevents some of that stuff as well. Experimentation. So if you basically just try to train a network with all possible variations that you want to test, and you see which one performs better. I think Kelly has a parameter study that he did that was like several months of compute across 16 or 24 GPUs, just to figure out like how much attention, how far the attention should go, and how big the size of the inner nodes of the network were and stuff. That's when people say that machine learning is like an art, not a science. Like that's what they mean. Like you sort of like there's not a scientific like you can't go, oh, well, this problem has the data size of X, so I need a model size of 2X, right? There's. All right, thanks everybody.